Students, this is Dr. Mohga, and today we're going to be talking about speed, velocity, and acceleration. Today we're going to learn a couple of things. We need to know the difference between distance and displacement, the difference between speed and velocity. We need to know the graph of speed and velocity, be able to analyze it and get answers from it. We need to know what's acceleration, its equation, and its graph, and be able to analyze it as well. Let's start with the difference between distance and displacement. Distance is nothing but the length from one point to another. It's a scalar quantity, which means that it has only the magnitude. Since I'm only measuring my length, like 20 kilometers, 20 kilometers has no direction, so it's a scalar quantity. If you're measuring time, 2 hours, 5 minutes, 3 seconds, did I mention any direction? No. Then time is also a scalar quantity. Distance is measured in meters or kilometers. As for displacement, displacement is just like distance, but it also has the direction. So in this case, I'll say 20 kilometers north, or 5 steps or 5 meters to the left. So if I'm including my direction with the magnitude, then we call it a vector quantity. Just like distance, displacement is measured in meters and kilometers. Now let's look at this example. Here we have a car that drove 20 kilometers to school and then went in the opposite direction and made a stop after 10 kilometers. So if I want to get the distance, I'll get the total length, which is 20 plus 10 equals 30 kilometers. If I want to look at displacement, then I will do plus 20, which is my forward direction, minus 10, which is my backward direction, which will give me 10 kilometers. Like we said, displacement is how far you are from the start point and in which direction. So if I want to know the direction, I will say to the left or to the right. I will start from where the car was to where it stopped in the end. So this is to the left. Speed and velocity, just like distance and displacement, they're very similar. Speed is the distance traveled per unit time. Since it's the distance traveled per unit time, if my distance is in meters and my time is in seconds, then speed will be in meters per second. If my distance is in kilometers and my time is in hours, then my speed will be in kilometers per hour. As you can see, we said it's with distance, so I did not mention direction, so therefore speed is a scalar quantity. On the other hand, velocity is displacement over time. Displacement, if you recall, was distance with direction. So velocity is scalar or vector? It's definitely a vector quantity because it has direction. It's also measured in meters per second or kilometers per hour. Let's use the same example we used in the previous slide. Here we said that the total distance was 30 kilometers and the total displacement was 10 kilometers to the left. If I want to get my speed and velocity, now that they've shown me that the time was 2 hours, I will say that speed is distance over time, which is 30 over 2, giving me 15 kilometers per hour. Velocity is displacement over time, which was 10 kilometers to the left over 2, giving me 5 kilometers per hour to the left. Here are 2 examples. You may pause the video to do them on your own and then unpause to check the answers. A truck travels 110 kilometers in 2 hours. What's the average speed of the truck? Speed is distance over time equals 110 over 2, giving me 55 kilometers per hour. Jessie throws a ball that moves at an average speed of 35 meters per second and travels for a total of 4.5 seconds. Work out the distance traveled by the ball. You have to use the same equation, which is speed equals distance over time, but rearrange it to find distance. So now my distance will be equal to speed times time. So my distance is going to be speed times time, which is 35 times 4.5, giving me 157.5 meters. Here's another example. Again, you may pause the video, try it on your own, and then unpause to see the answer. A car travels at an average speed of 50 kilometers per hour. How long will it take for the car to travel 12.5 kilometers? Give your answer in minutes. How long then they need my time? Speed is distance over time. Rearrange your equation. Time will be equal to distance over speed. The distance here is 12.5 kilometers and speed is 50 kilometers per hour. So 12.5 over 50 will give me the time in hours as 0.25 hours. The question told me to give the answer in minutes. So once I find my answer in hours, I have to convert to minutes by multiplying by 60. So 0.25 times 60 is 15 minutes, and that's my final answer. Another example, again, pause the video, try it on your own, and then unpause. The distance from the Sun to Mars is approximately 210 million kilometers. Remember, million has 6 zeros, so I can simply write it as 210 times 10 to the power of 6. What is the speed of light in kilometers per second if it takes 11 minutes and 40 seconds for light to reach Mars from the Sun? First step, I need to convert my time fully into seconds. So I'll do 11 times 60 to convert my minutes to seconds, and then plus 40 to have the total time in seconds. Now that I have the distance and I have the time, I can get my speed with our equation. Speed equals distance over time, which is 210 times 10 to the power of 6 over the time, which is 700 after conversion, giving me 300,000 kilometers per second. Next, we have the distance time graph. In the distance time graph, we need to know two things. Number one, we need to understand the graph. And number two, we need to be able to calculate using the graph. Let's start with the first part. In the first part, they're giving me distance, which is on the y-axis, and time, an hour, on the x-axis. As you can see, the slope is going up in a straight line. Distance is increasing, time is increasing. So this is constant speed. Then I have a horizontal line at 30 miles from time 13 to time 13:30. So the horizontal line, you can see that the distance is not changing. That person stopped at the 30 miles, yet the time is passing, which means he's stationary or at rest. Then I got a slope again in a straight line. So the slope shows constant speed. And once again, the distance stops at 40 miles, but the time continues to go for a full hour. So the person is stationary or at rest. In the last part, the slope going back to the origin, back home, at a constant speed, since it's a straight slope, of 40 miles per hour until they go all the way back to distance 0. Before we solve this example, let me go back to the previous slide. Just to remind you that you may be asked, for example, what is the distance when the time is 13.00? So at 1 p.m. at 13:00, I will draw a line, a vertical line from 13, go all the way up until the graph, and I will see the distance stopped at where? So at 13 exactly, the distance has stopped at 30 miles. Vice versa. If I ask you, at 35 miles, what was the time? So you're going to go to the distance in the y-axis, mark 35 between 30 and 40, and draw a line using your ruler. Never draw with a pen without a ruler or a pencil without a ruler. Use a pencil, use a ruler, and draw a line. And you're going to find that the time was at somewhere around 13:40. Now let's look at the example. Please take a minute, pause the video, try to solve it on your own, and then unpause to check the answer. The question says figure 1.1 shows the distance-time graph for a student. The student walks out of a classroom, stops to talk to some friends, and then walks to their class. First, before I even look at the questions, I need to analyze the graph using the information given. The graph starts at A, and it says the student walks out of a classroom. So from A to B, the student is walking out of the classroom, stops to talk to some friends. So from B to C, as we said, it's stationary. So this is where he stopped to talk to some friends. And then walks to their next class. So from C to D, they're walking to their next class. Now let's read the questions. Describe the motion of the student between time 0 and time 6 seconds. This is constant speed where the student is walking out of the classroom. Part B, calculate the speed of the student between time 0 and time 6. From 0 to 6, we said speed is distance over time. Here you need to find the gradient. And gradient means if I have starting and ending point, I will calculate it by subtracting the ending by the starting point. So speed is distance over time. My distance will be 12 minus 0. This is the start and end point. And the time will be 6 minus 0. That's my start and end point. So speed is 12 over 6, which will give me 2 meters per second. Determine the length of time for which the student stops walking. When did he stop walking? As we said, from B to C. So that's from 6 to 11. So this should give you 5 seconds. Part D, compare the student's speed in section AB with the section CD. Here, this part is very, very easy. The more I have my graph towards the slope is towards the y-axis, the steeper it is, so therefore it is faster. Okay? So the more steep my graph is, the faster something is moving. All right. Let's look at this part. At this part, for the next section, which is acceleration, acceleration is nothing but velocity over time. It's measured in meters per second squared. Why is it measured in meters per second squared? Because velocity is in meters per second and time is in second. So putting them on top of each other will give me meters per second squared. If someone is speeding up, we call this acceleration, and if they're slowing down, it's deceleration. What if they are at constant speed? Are they going faster or slower? No, they're not. So at constant speed, I have no acceleration. My acceleration will be equal to 0. Before we move on to an example about acceleration, we need to talk about the acceleration of free fall. Since if something is changing speed per time is acceleration, then falling is also acceleration. What if nothing holds you back? No friction, no air resistance, nothing is holding you back. We call this free fall, and the only force that's available here or that's acting is gravity, pulling you down. On Earth, gravity gives every freely falling object the same constant acceleration, which is 9.8 meters per second squared. So if I want to get my free fall at, let's say, 50 meters, it will be 9.8 meters per second squared. At 20 meters, 9.8 meters per second squared. So does it matter how far I am from the ground? No. If there is no friction, no air resistance, they have to tell you this in the question, then my acceleration of free fall does not change. Falling in a uniform gravitational field. First case, we have falling without air or liquid resistance. If I'm in vacuum, no resistance force is acting, only gravity. So all of the objects are falling at the same acceleration, which is 9.8 meters per second squared. The speed would increase uniformly, which means that there will be constant acceleration. Now, second case, if falling with air or liquid resistance. Now, this is no longer free fall, right? If I have any kind of resistance. So as the object falls, air or fluid pushes against it. This is a resistive force, which is also called drag. The resistance, the faster you go, the more there will be air resistance. So eventually, you'll reach a point where the upward resistive force becomes equal to the object's weight. At this point, the upward force, which is the air resistance, will be equal to the downward force of your weight. So the air resistance and the weight will be equal. So what is my net force? 0. So if I have air resistance force of, let's say, 15 Newton up, and my weight, like we said, is 15 Newtons down. So since they're opposing, plus 15 and minus 15, it's going to give me 0. So at this point, the net force is 0 and the acceleration is 0. At this specific point, when they are equal, we call this terminal velocity. So this constant maximum speed is known as terminal velocity. The object continues falling at constant speed from this point onward. Next, let's talk about falling in a uniform gravitational field. At the start of a fall, like we said, air resistance is very, very little and the weight is much, much higher. So the object or the person accelerates as they're going down. As their speed increases, the air resistance starts to become more, almost reaching the same amount of weight. So the acceleration starts to decrease one by one, slows down, until they reach a point where the weight and the air resistance are equal, like we said, terminal velocity. And here I'm at constant speed with 0 acceleration. Here's an example. You may pause the video, try it on your own, and then unpause. An object falls towards the surface of the Earth. The object is falling at its terminal velocity. Which statement is correct? There is air resistance and acceleration of object is negative. There is air resistance and acceleration is 0. No air resistance, but the acceleration is negative. No air resistance and the acceleration is 0. Of course, since we're at terminal velocity, then there will be air resistance equal to my weight, and the object's acceleration will be 0. Here's another example. Please pause the video, try it on your own, and then unpause. A small object falls out of an aircraft. Choose words from the list to complete the sentences below. The weight of an object is the product of the object's mass and the, of course, gravitational field strength. When an object falls, initially it accelerates. As the object falls faster, the force of air resistance acting upon the object increases. Eventually, the object falls at a steady speed when the force of friction equals the force of weight acting on it. If I may, I just want to highlight something. Some people confuse gravitational field strength with gravitational force. They are not the same. Weight is a force. Gravitational field strength is weight over mass, or it's also considered something which we're going to study later, but we've taken it with acceleration as 9.8 meters per second squared. So gravitational force is a force just like weight. Gravitational field strength is the pull of gravity on a certain planet or an object, and on Earth it's 9.8 meters per second squared, like we've taken it. So do not confuse the two terminologies, they are not the same. Next, we have the velocity time graph. Always look at the labels at the y-axis and the x-axis. They are very important because you're going to see some things that are very common but are explained or analyzed differently. Here, the person is increasing the velocity with time. So they are accelerating. Then they are maintaining a certain velocity with time. They do not stop. There's still velocity, but it's constant. So here there's a constant speed. Then we have, again, acceleration in the black line. And at a certain point, there is decrease in velocity. So we call this deceleration. At the negative gradient, it's known as deceleration. We need to know three things in the velocity time graph. Number one, just like we did right now, you need to be able to analyze the graph. Number two, you need to know how to get the velocity if they give you the time if they give you the velocity, acceleration if they give you velocity and the time. And third of all, you need to be able to find the distance from a velocity time graph. So here, we're going to have the equation to calculate the distance. The equation to calculate the distance, we have two scenarios. Scenario number one, if I have, for example, they tell you, find the distance traveled in the first 4 seconds. Immediately at 4, like we've said before, I'll draw a line with my pencil and the ruler. And I will look at this shape. What shape is this? This is a triangle. So to get the distance traveled in this part, this triangle, I will need to use the law for finding the area of a triangle, which is half times base times height. And this will be my distance. So if I have a 90 degrees triangle or a right angle triangle, I'll use half times base times height to get my distance. In the red triangle that we just highlighted now, half times base, my base is 4, times height, my height is 3. So my distance in this triangle will be half times 4 times 3, which is 6 meters. My second law is for a rectangle. If I was asked to find the distance traveled from 4 to 6 seconds line, this is a rectangle. I'll use the area of a rectangle, which is base times height. So here my base is 2, from 4 to 6, that's 2. And my height is 3. So 2 times 3, so my distance is 6 meters. Okay? What if I want to find acceleration? I will get the gradient, like we talked about it before, the 2 points. Since acceleration is velocity over time, so if I want to find the acceleration, for example, until at 4 seconds, from 0 to 4 seconds. So what I'm going to do is I'll do final velocity minus initial velocity over final time minus initial time. My final velocity was 3. My initial velocity was 0. So 3 minus 0. My final time was 4. My initial time was 0. So 4 minus 0. So it's going to give me 3 over 4. Of course, you need to convert this to decimal because in physics, we always keep our answers in decimal figures. Here's another example. They want us to find the total distance. So you need to divide this drawing into either one of the two shapes we talked about, either right angle triangle or rectangle. Here, he divided it with the dashed lines, as you can see. So what they've done is, for the first area, they found the area of the triangle AOH, and this is a triangle, so half times base times height, so half times 10 times 15, which is 75 meters. For the second area, which is this rectangle, ABGH, ABGH is a rectangle, so base times height, from 10 to 20, that's 10, and the height is also 15, so it's going to give me 150 meters. The third area, he wants to find the triangle BCI and the rectangle BIFG. For BCI, it's a triangle, so half times base times height, which is half times the base is from 20 to 30, so that's 10. And the height is from 15 to 25, so that's another 10. So half times 10 times 10. For the rectangle BIFG, I'm going to do base times height. My base is 10, and my height is 15. So 10 times 15. Hence, the answer is 200 meters. Next, I have this big triangle, CFE. So half times base times height, half times base, from 30 to 50, that's 20. And the height is 25. So half times 20 times 25 is 250. Now he asked me to find the total distance. So I will add the 4 distances I found together to get 675 meters. Here's the last example. I need you to try it on your own. Pause the video, try it, then unpause again to check your answer. Figure 1.1 shows the speed time graph for a ball falling through the air. Determine the speed of the ball at time 1. So at 1, I'm going to draw a straight line and then find my speed, just using the graph. So the answer is going to be 3.55. For the second part, describe the speed of the ball between 2 and 5 seconds, so between 2 and 5 seconds. I need the speed. What is the speed? Well, the speed did not change at all. As you can see, it's a horizontal line. So I'll just say constant speed. Now, for the third part, calculate the distance. Distance in a speed-time graph. Immediately, if I see distance in a speed-time graph, then I need to get the area under the graph. Between 2 and 5 seconds. 2 and 5. That's a rectangle right there. So I'm just going to do base times height. And that's going to be 3 times 4, which is going to give me 12. That's all for today. I hope the lesson was easy and clear. If you have any questions, please let me know. Thank you very much and have a good day.